Hi again, this is Tzvi, and today's lecture will be about trigonometric integrals, which corresponds to chapter 7.2 in Stewart's calculus. Okay, so whenever you're talking about trigonometry, a good place to start is the Pythagorean Theorem. And we'll restate it here for the record. Let A and B be the legs of a right triangle, and C its hypotenuse. Then A squared plus B squared equals C squared. And you can see here that C corresponds to the hypotenuse of this right triangle here. And that indeed the sum of the red square and the blue square's areas is equal to the area of the green square. But we're not going to be too occupied with this proof. We're just going to take the Pythagorean theorem and deduce some properties of trigonometric functions. So we're starting with this model right triangle. We have theta in the bottom left corner here, and the legs A and B, and hypotenuse C. And we're going to deduce a number of identities. So the first thing we can do with A squared plus B squared equals C squared is divide through the whole equation by C squared. When you do this, you get what you see in number 1, which is A over C squared plus B over C squared equals 1. And since A over C is the sine of theta, and B over C is the cosine of theta, we get sine squared plus cosine squared theta equals 1. Similarly, we can divide through the whole equation by B squared. When we do that, we'll get tan squared theta plus 1 equals secant squared theta. And just rearranging a bit, we get secant squared theta minus tan squared theta equals 1. Finally, we get a version with cotangent and cosecant. We're not going to be working with those at all in this lecture, but it's the same idea. You just divide through by A squared. You get 1 plus B over A squared equals C over A squared. Kindly disregard this equals 1. And in other words, that's just 1 plus cotan squared equals cosecant squared theta, or cosecant squared theta minus cotangent squared theta equals 1. Okay, so those are our useful Pythagorean identities. The other trigonometric identities, which will be somewhat useful, are double angle formulas. And double angle formulas are as follows. We have sine of 2 theta equals 2 sine theta cosine theta, and cosine of 2 theta equals 2 cosine squared theta minus 1. Okay, we can apply a Pythagorean identity to get the other two as well. That equals 1 minus 2 sine squared theta and cosine squared theta minus sine squared theta. And we can get another set of identities for the squares of sine and cosine using that second line. We'll deduce that sine squared theta equals half of 1 minus cosine 2 theta, and cosine squared theta equals a half of 1 plus cosine 2 theta. And these will be useful when we have powers of sine and cosine in our integrand, and we want to make them smaller powers. Okay, we can substitute this expression, which just has a power, a cosine to the 1, even though the inside of the cosine is different. It's cosine of 2 theta, but it's just cosine to the 1, and that replaces something that has an even power. Okay, so keep those in mind as we go through. We're going to be using Pythagorean identities a lot and an occasional double angle formula. Okay, so here's our general strategy for trig integrals. We're going to be solving integrals of the form sine to the m of x, cosine to the n of x dx, and the integral of secant to the mx, tangent to the nx dx. And our typical strategy has 2 steps. First, you make a u-substitution, so that after removing the du, we have an even power of the non-u function. Okay, so if our u was sine, then we want to make sure that whatever cosines are left come in even powers. Okay, so it'll be cosine squared or cosine to the 4th, etc. Once you've made that u substitution, you want to use the Pythagorean identities to translate the non-u functions into u's. Okay, so in that example where you substitute u equals sine x, you want to use the fact that cosine squared x equals 1 minus sine squared x to turn all of your cosines into sines. Okay. An important remark here is that there are cases where this is not possible, and then you'll have to use other tricks. And there are also cases where you can make different u-substitutions that are both valid, but one is much simpler. And we'll see all of this. Okay, but let's start with an example of sine to the m cosine to the n. So our particular example here is sine to the 10x times cosine to the 5x dx. And you'll remember the first step of our strategy is make a u-substitution so that after removing du, we have an even power of the non-u function. So let's try it with u equals cosine of x. If that was the case, then du would be minus sine x dx. And the integral that remains after factoring out the du would be minus sine to the 9th x cosine to the 5th x times minus sine x dx. Okay, so this isn't great because our whole objective is to make sure that the non-u function, and here the non-u function is sine, we want to make sure that that appears to an even power. And here it appears to power 9, which is not even. So we're going to reject this option. We do not want to use u as our, we do not want to use u equals cosine x. So let's try u equals sine x. Okay, if the u is sine x, then du is cosine x dx. And our integral becomes the integral of sine to the 10x cosine to the 4th x cosine x dx. Okay, and we want to check that the non-u function, here u is sine, so our non-u is cosine, appears to an even power, and 4 is even. So we're all set. Okay, so this is our desired u-substitution. Once we've done that, we want to use Pythagorean identities to translate the non-u function into u's. So again, our u was sine x. And the integral that we're left with is sine to the 10th x cosine to the 4th x cosine x dx. Okay? And this was, of course, du. du is cosine x dx. So, given that cosine squared x is equal to 1 minus sine squared x by the Pythagorean identity, we can square both sides of the equation and maintain identity. Something that's false, and I want to encourage you not to do this, false, you can't just change the power. Okay, so cosine to the 4th x equals 1 minus sine to the 4th x. Okay, this does not work. You want to make sure that you're squaring or applying whatever is the necessary power to both sides of the equation in a consistent way. Okay, because as you'll see when we expand this, we get 1 minus 2 sine squared x plus sine to the 4th x. Right, and that's plainly not the same as 1 minus sine to the 4th x. Okay, but we can plug this in. So we have this integral becomes sine to the 10th x, sine to the 10th x times 1 minus sine squared x squared times cosine x dx. Now we can make our u substitution, and we have this is equal to u to the 10th times 1 minus u squared squared times du. Okay? I'm going to add an extra page in here. So we were just at u to the 10th times 1 minus u squared squared du. And we'll multiply out as we had above. So it's u to the 10th times 1 minus 2u squared plus u to the 4th du. And that's equal to u to the 10th minus 2u to the 12th plus u to the 14th du, which is u to the 11th over 11 minus 2u to the 13th over 13 plus u to the 15th over 15 plus c. Okay, so obviously our problem was originally posed with x's, so we need to convert back using our u substitution. So this is sine to the 11th x divided by 11 minus 2 sine to the 13th of x divided by 13 plus sine to the 15th of x divided by 15 plus c. And that's the solution to our integral. So again, those two key steps there are finding the right u substitution by checking which u substitution leaves an even power of the other function, and then using the Pythagorean identity to turn that other function into your u. Okay, let's see another example. This is also of the form sine to the m of x cosine to the n of x, and it's an example where both u substitutions are possible. So let's consider what would happen if we do u equals sine x. Okay, then we know that du equals cosine x dx. And our integral that we would be left with would be sine to the 3rd x cosine to the 8th x, cosine x dx. Okay? And this actually works because we have, looking at the non-u function, which in our case is cosine, we have an even power here to the 8th. Okay, let's see what happens with the other u substitution that's possible. We could substitute u equals cosine x. Then again, du is minus sine x dx. And the integral becomes integral of sine squared x cosine to the 9th x. We should put a minus sign here, minus sine squared x cosine to the 9th x times minus sine x dx. Okay, we put a minus sign in front to cancel with this minus sign. And again, our non-u function is sine. And here we have an even power of 2. Well, which one of these is preferable? As soon as we do the u substitution here, we have u cubed, let me stay consistent about colors. We have u cubed times 1 minus u squared to the 4th du. Okay, and that's because this is the 4th power of cosine squared. Whereas on this side of the this option, we would end up with minus 1 minus u squared times u to the 9th du. And here, this is not raised to any power at all. So all we'll have to do is distribute. We'll take, minus u to the 9th plus u to the 11th. Here I have to expand the 4th power of 1 minus u squared, which would be quite a lot of work. So we're going to opt for this one. Okay, now on the next page, we're going to look back at the trigonometric form of this. So this is minus sine squared x cosine to the 9th x minus sine x dx. And this, as we said before, it's going to translate into u's very nicely. We just have the sine squared x is equal to 1 minus cosine squared x, which is 1 minus u squared. And we're left with minus the integral of 1 minus u squared u to the 9th du, which is minus the integral of u to the 9th minus u to the 11th du. And we'll see the conclusion of that on the next page. And here, as I pointed out in the last page, I'll just start it again here. If we were to expand this, we would have the integral of sine cubed x cosine to the 8th x cos x dx. This is going to require cosine squared x equals 1 minus sine squared x, which is 1 minus u squared. So cosine to the 8th x equals 1 minus sine squared x to the 4th power, which we can just put u in here to make it a bit simpler. 1 minus u squared to the 4th power, and that's going to be something really ugly like this. 1 minus 4u squared plus 6u to the 4th plus 4u to the 8th, plus 4u to the 6th, my apologies, minus u to the 8th. Okay, so that's going to be very, very annoying to put into our integral. So we're going to, as we said, we'll stick with this one. Okay. So let's just finish up this integral. So we had minus the integral of u to the 9th minus u to the 11th du, and this is equal to minus u to the 10th over 10 minus u to the 12th over 12 plus c, and we get minus, and now we'll just apply the minus sign, so the 12th power now is positive, so we'll start with that. Cosine to the 12th x divided by 12 minus cosine to the 10th x divided by 10 plus c. Okay, and yeah, the c picks up a minus sign, but because it's an arbitrary constant, that's something we can ignore. Okay, so just to summarize, we saw a problem here where both u substitutions were possible, but one was much nicer. One required a lot less multiplying out large powers, and so we chose that one. There are also times where neither u substitution works for you. And in those cases, we'll use double angle formulas, which we saw earlier in the talk, to reduce the powers of the integral. Here's an example where that happens. We're asked to compute the integral of sine squared x cosine squared x dx. What would happen if we tried to do a u substitution here? So let's say u equals sine x. Well, in that case, du would be cosine x dx, and we'd be left with sine squared x, cosine x, and cosine x dx. And then we'd be left with an odd number, an odd power of the non-u function. So we wouldn't be able to convert the cosines into sines. So this doesn't work. On the other hand, if we try u equals cosine x, we run into the same problem. We'll have du equals minus sine x dx, and our integral becomes minus sine x. Okay, we pick up a minus sign when we factor out this du, minus sine x cosine squared x times minus sine x dx. And here again, we have our non-u function appearing to an odd power. So we can't use this. We won't be able to convert that into a power of cosine. Okay, so given that neither of these are possible, we're going to clear this. So given that neither of those are possible, we have our integral sine squared x cosine squared x dx. We're going to apply the double angle formulas. And recall that those are sine squared x equals 1/2 times 1 minus cosine 2x, and cosine squared x is equal to 1/2 times 1 plus cosine 2x. Okay. So plugging that into our integral here, we get that the integral equals integral of 1/2 1 minus cosine 2x times 1/2 1 plus cosine 2x. And that's with dx at the end. Now let's simplify. We can bring these constants out in front without changing the value of the integral. So we have a quarter up here. And now you'll notice that this is of the form a plus b times a minus b, which is the difference of squares. So we can just turn this into 1 minus cosine squared 2x, apologies. Dx. Okay, well here we run into our same problem. This is an even power of cosine, and there's no u substitution that we're going to be able to make to simplify this. So we're going to apply the double angle formula again. This time we have cosine squared of 2x equals 1/2 times 1 plus cosine 4x. Okay, and plugging that in, we get 1 minus 1/2 1 plus cosine 4x dx. Okay, let's box this in with green, and we're going to simplify this a bit. This is quarter of the integral of, well, we have 1 minus 1/2, so that will just end up being 1/2 minus 1/2 cosine 4x dx. Okay, so we can even factor out another half here to simplify our lives, and we get 1/8 times the integral of 1 minus cosine 4x dx. So the first term, 1, when you integrate that, that's just x. Let's get 1/8 x minus the integral of cosine 4x dx. And here we could do a u substitution, or you could just eyeball it if you're comfortable with that. Our u substitution would be u equals 4x du equals 4 dx. And because we have dx here on its own, we'll just make that du over 4 equals dx. So our integral becomes 1/8 times x minus the integral of cosine u times du over 4, which is 1/8 times x minus 1/4 sine of u. And we know sine of u is, and we know u is 4x, we just plug that in, 4x plus c. Okay, so after all of that, we have our answer. It's x over 8 minus 1 over 32 sine of 4x plus c. Okay. was a tricky problem, but worthwhile, I think. And let's add in one more slide here and just double check that that's truly the correct integral. So if we take this, we're going to copy that and insert it here. So I am going to double check that when we take the derivative of this function, we get sine squared x cosine squared x. Okay, so let's see what happens when we take the derivative. This becomes 1/8 minus 1/8 sine, that should be cosine 4x. Okay. And that's because the x over 8 gives us 1/8 the sine 4x. Applying the chain rule, we have cosine 4x times 4, and then the 4 cancels with the 1 over 32 to give us minus 1/8. Okay, now we can apply the double angle formula again. We get, this is 1/4 of 1/2 times 1 minus cosine 4x, which is exactly 1/4 of sine squared 2x. Okay. And now applying the other double angle formula that we're familiar with, sine of 2x equals 2 sine x cosine x, and plugging that in here, we'll get 1/4 times 2 sine x cosine x squared, which is 4 sine squared x cosine squared x, and the 4's cancel, and we're left with sine squared x cosine squared x, which is exactly what we were hoping for. Okay, great. So even though this function with the x over 8, it looks maybe like it shouldn't be the integral of a trig function, it absolutely is. Okay, now let's get to secant and tan. So it's the same strategy, just with a different u and du. Okay, our example here is secant cubed x tan to the 5th x dx, and we want to make a u substitution so that after removing du, we have an even power of the non-u function. Okay, so let's do that. Let's try each relevant u. So if we were to take u equals secant x, we know du would be secant x tan x, which is the derivative, dx. Okay, and that would mean that the integral becomes the integral of secant squared x tan to the 4th x times secant x tan x dx. And this actually looks pretty nice. We have an even power of both functions. All we need it for is the tan, because we need to convert the non-u function, i.e. the tan, into the u. What would have happened if instead we did u equals tangent x? So if u equals tangent x, then du would be secant squared x dx, because that's the derivative of tangent. And our integral becomes integral of secant x tan to the 5th x times secant squared x dx. Okay, so this is a problem for us because our non-u function now appears to an odd power. And that means we can't turn it into tangent. We can't use the Pythagorean identities. Okay. And that's why we choose u equals secant x as our u substitution. Okay, so given that this is the integral that results from choosing u equals secant x as our as our u substitution. We want to remember that we want to turn our tangents into secants. So because of the identity secant squared x minus tangent squared x equals 1, what that means for tangent squared, if I want to substitute it, if I want to turn it into secants, I'll add tangent squared to both sides and subtract 1. I get tan squared x equals secant squared x minus 1. And if we want tan to the fourth, then we'll just make this to the fourth and we'll square this side. Okay, and because secant is our u, this becomes u squared minus 1 squared. Okay, plugging that in, we have the integral of u squared times u squared minus 1 squared du. This is equal to, and I'm going to box this off here. This is equal to the integral of u squared times u to the fourth minus 2u squared plus 1 du, which is equal to u to the sixth minus 2u to the fourth plus u squared du. And now we can take the antiderivatives. This is u to the seventh over 7. This is just applying power rule. Minus 2u to the fifth over 5 plus u cubed over 3 plus c, where c is our constant of integration. And now we can plug our u back in. So this is equal to secant to the seventh of x over 7 minus 2 secant to the fifth of x divided by 5 plus secant cubed of x divided by 3 plus c. Okay, again, same idea. Look for the u substitution that leaves you with an even power of the non-u. And then once you do that, apply the Pythagorean identities to turn everything into u's. Okay, just like with sine and cosine, sometimes both u substitutions are possible for a secant and tan problem. So let's see what that looks like here. So we have the integral of secant to the fourth x tan to the seventh x. So if we take u equals secant x, then du would be secant x tan x dx. And we're left with our integral becomes integral of secant cubed x tan to the sixth x secant x tan x dx. Okay. Meanwhile, if we take u equals tangent x, we have du equals secant squared x dx. And our integral would become secant, so the integral of secant squared x tan to the seventh x secant squared x dx. Okay, so now in this integral, in the integral that the u substitution that we just did with u equals tan x, we want the non-u to appear to an even power. This is our non-u, and this is an even power, so we're good. Similarly, in the last u substitution, u equals secant x, we want the non-u to appear to an even power. Our non-u is tangent, so that also works. Okay, but you probably have a hunch that since this non-u appears to the power 6, whereas this non-u appears only to the power 2, this is better. And indeed, that's true. So here are the two different u substitution possibilities. So if we were to try to do this u substitution, we would say, well, tan squared x is equal to secant squared x minus 1, or u squared minus 1. So tan squared x, if we cube it, which gives us tan to the sixth, that'll be u squared minus 1 cubed, which is u to the sixth minus 3u to the fourth plus 3u squared minus 1. So it's a lot of multiplication you have to do. Whereas over here, if I take u equals tangent x, and then we're looking at converting the secants into tangents, we have secant squared x equals tangent squared x plus 1, or in other words, u squared plus 1. And then we're done because we only have secant squared. So our integral will be the integral of u squared plus 1 times u to the 7th du. So this is obviously preferred. Okay, let's finish this up. This will be u to the 9th plus u to the 7th du, or u to the 10th over 10 plus u to the 8th over 8 plus c. And plugging back in for u equals tangent x, we have tangent to the 10th of x divided by 10 plus tangent to the 8th of x divided by 8 plus c. Okay, so there's an example where we could have done either u-substitution, but we chose one which was simpler because the non-u function was raised to a lower power. Okay, and here we're missing a integral sign. There are also cases where neither u-substitution is possible, and then it'll be just ad hoc methods. I wouldn't expect to see a problem like this on the exam. So here's an example of secant x. You can't really plug in any u here, whether u equals tangent or u equals secant. But what you can do is you could realize, you know what? This is dx over cosine x. Okay. And oh, you know what? I thought I was going to give you a different integral. let's do this one. So this one is actually much more complicated. So if we multiply both top and bottom here by secant x plus tangent x. Okay, so because you're multiplying top and bottom by the same thing, it doesn't change anything. It's like multiplying by 1. The integral stays the same. But what you'll notice is that on the top you have secant squared x plus secant x tangent x divided by secant x plus tangent x dx. And you'll notice that the top is actually the derivative of the bottom. So we can take u, let's make a u substitution in a different color, u equals secant x plus tangent x, and du will be secant squared x plus secant x tangent x dx. And this integral becomes the integral of du over u, which, as we all know, is ln of the absolute value of u. And in our case, that's ln of the absolute value of secant x plus tangent x. Okay, this is not plus c, of course. This is not something I would expect you to be able to do on the fly, but it's one of the kind of, you can get a sense that there are tricks that you can do to get these trigonometric integrals that don't play by the rules. Okay, this one is a little bit easier. So here, and again, the integral sign went missing. This integral, you can also look at it as sine x over cosine x dx. And this, you have a much simpler u substitution. If you do u equals cosine x, then we get, and if, here, let me box this off, and du equals minus sine x dx, then we have, this is equal to the integral of minus du over u, which just will be minus ln of absolute value of u, or minus ln of absolute value of cosine x, plus c, of course. If you prefer not to have the minus sign here, you can use the log identities to get that this is actually equal to ln of the absolute value of secant x plus c. Okay, and then you have the secant x making an appearance, which we always like to see together with the tangent. This is another atypical case of integrating secants and tangents. And finally, just to finish off the chapter, there are examples where we have a product of sines and or cosines with different arguments, meaning things that you put inside of the function. So you have sine of 4 times x times sine of just normal x, or sine of 5 times x times cosine of 3 times x. And similarly, cosine of 6 times x times cosine of 2 times x. And for these examples, we use the product to sum formulas, and that allows us to turn a product of two trig functions, in particular sines and cosines, into a sum of those trig functions, which makes them much easier to work with. Okay, so here we're asked to compute the integral of sine of 4x times sine of x dx. So we'll look back at our table of formulas. We know that sine A sine B is half of cosine A minus B minus cosine A plus B. Okay, so this will be equal to 1/2 cosine of A minus B. So in our case, that's 3x minus the cosine of A plus B, which is 5x. Okay, dx integral, this is much easier to do. We'll have a half of 1/3 sine 3x minus 1/5 cosine, sorry, it should be sine, plus c. Okay. So once we get it in this form, it's relatively straightforward. You can do if you'd like, you can split it up into two integrals, cosine 3x and the integral of cosine 5x, and then do a u-substitution, or you can kind of use the patterns of how these functions are integrated to get this expression. Let's take a different formula, a different integral. If we want to compute the integral of sine of 5x times the cosine of 3x, I look up at sine A cosine B, which is equal to 1/2 sine A minus B plus sine A plus B. So this equals 1/2 of sine A minus B, which is 2x, and we want to do a plus sign, plus sine of 8x, and we're taking the integral of that, and what we get is 1/2 times 1/2 of minus cosine 2x minus 1/8 cosine 8x plus c. And I think that's a good place for us to stop. Again, a lot of this is just a matter of finding the right u-substitution that makes the rest of the problem flow nicely. Thanks so much.